talking about geophysics. And this is related to geology because you're talking about the Earth, you're talking about Earth processes, you're talking about all these things that are still related to geology, but you're applying it in a different way. You're using math and physics and all these other things in conjunction with geology. So some of the things that we're going to learn in this lecture is how seismic waves behave as they pass through the Earth's interior, what the study of seismic can tell us about layers of the Earth, and that the Earth has a gravitational and magnetic field that can be measured for understanding anomalies. And there's different tools and devices and equipment that we can use for geophysical methods. So what is geophysics? Geophysics is the non-invasive study of the subsurface. And what I mean by that is when we've talked about geology, it's usually about what we see at the surface and how we can deduce things about what's happening in the surface or in the subsurface based on what we see. Now, when we talk about how we can find out more what's beneath our feet, we talk about drilling wells for groundwater, and we can look at samples, rock samples, and things like that. Now that's invading the subsurface. But how do we get a sense of what's beneath our feet without drilling anything, without digging anything? And that's what geophysics is. So there's all these different types of data that can be acquired to study the subsurface, to see what lies beneath, basically. We have seismic, we have ground penetrating radar, we have DC resistivity, a device called a gravimeter, and a magnetometer. So all these things measure different properties of the subsurface without actually physically digging out any of the subsurface. And that's what makes geophysics such a cool and robust tool, is that we can see things beneath the surface. A little bit about this already in the context of earthquakes, and we've talked a little bit about this in the context of plate tectonics and the Earth's interior. So seismic data is basically where these little earthquakes occur in the subsurface, and they create a sound wave that can be measured by a device called a seismometer. Again, we think of this as it relates to earthquakes, but what we can do is we can basically induce our own earthquake or create our own source of sound waves that can be measured in the subsurface. So these acoustic waves spread radially from the source, be measured at receivers to determine things about the subsurface. We can infer things like the velocity, the density of the rock, perhaps if there's fluids there. So how this works is we can acquire seismic data using, on land, we would use a vibroseis. If this were done in the ocean, we would use floaters on top of the ocean, or you can also set them at the bottom of the seafloor. But for this simple purpose, let's look at our source being a vibroseis. And this is a truck that couples with the Earth, and it shakes the Earth at a sweeping range of frequencies. So away from our source is we have our receivers. These are called geophones. Now, this is also sort of like a seismometer, and it measures how much the Earth is moving, in which directions it's moving. So the vibroseis starts off with a sweep of frequencies. Like it's creating its own earthquake over here, okay? Then it penetrates out radially. And what this acoustic wave does is it hits layers in the subsurface and bounces off of them. And the receiver here measures how long it takes to receive that signal. And as there's different densities in the subsurface, they bounce at different angles, and it takes longer for them to get there. So as the geophones, or the distance between the source and the receiver, varies, like you see here with this example, we can see that it would take different time. It would take longer time for the source to reach the receiver that's further away. Now, as it bounces off a different layer in the subsurface, it would reflect differently. It would take a different amount of time. And so as you process this data. It's quite complicated, especially if you think about how the subsurface is so different. It's not often a layer cake that we see here, this perfect example. So you have all this math that goes into this. And what you do is you have this wavelet that radiates out radially with all these different frequencies, and it measures the time at the receiver it takes for this data to reach it. And so then there's all this math and programming and all sorts of stuff that goes in to creating a picture that we get of the subsurface. And this picture is what we interpret as a geophysicist. It's data that I would interpret to understand what the subsurface structures are like, or if there's fluids there, or if there's faults, things like that. And so, like I said, we in seismic data, it's a sweep of frequencies, and these are typically low frequencies in the scale of 20 hertz or so. So what does that mean in the context of other sound waves? Well, we can really only hear frequencies that range, I don't know, between 20 hertz and 20 kilohertz. If you've ever listened to a song and you can't quite hear, the super high frequencies, or you can't hear the super low frequencies, that's part of this range of why we only hear a certain amount of frequencies. So we're talking about seismic waves, what frequency those occur at. They recur at the far other end where we probably wouldn't even hear them because it's such a low frequency. Now, there's some other techniques that I'm going to show you that are at much higher frequencies. And again, we don't hear those either. So here's a quick video of how a vibrosize works and what it looks like. Image looked like beneath the surface, and it had a bunch of squiggly lines and colors. So part of that process is once that data is collected, then it goes through a lot of programming, a lot of things that you have to correct for. And some of these things are a bit out of scope of this class, but just so that you can see it and visualize it, there's a few different things that you have to do in order to correct this data. You have to think about how the wavelets behave in the subsurface. If you have to correct for topography, if you're taking this data, and there's a big hill, well, that's going to impact how the waves behave below it. So there's a lot of things that go into processing seismic data. Okay, just a little bit of math here. So when we look at a squiggle, I'm going to show you a squiggle in a second. Really what we're looking at is what's called as the acoustic impedance. And this is the product of density and velocity. And a change in acoustic impedance between rock layers affects the reflection coefficient. So if we look at, this is an example of the acoustic impedance, and each little tick here would represent a change in the density or velocity. And the acoustic impedance is really the image that we see as a result of seismic lines. It's a bunch of these little stick diagrams kind of added together. and squished together. And waves travel in the subsurface and attenuate with depth. So this makes sense if you think about it in relationship to other sound waves that you've had experience with. If I'm in a really echoey place and I yell and I go, echo, and it bounces off the walls and you can hear it. If you're in a really large room, you can hear your voice for a long distance. Now, if you've ever tried to yell underwater, you usually don't hear someone literally next to you in a pool trying to yell at you. And that's because sound waves get attenuated. That means that they don't travel as far. And so the same happens in the subsurface, is that we have attenuation with depth. And as these waves encounter things on the subsurface, they get attenuated. They don't travel as far. And there's a relationship to explain that. And it's proportionally represented as the wavelength is proportional to velocity and frequency. So the lower the frequency we are, the less wavelength that we have. And so that relationship helps us understand the resolution of our data. Okay, so here's a quick demonstration of some seismic interpretation. I just have a picture that I grabbed off the internet, and I will show you how you interpret it. When we look at this data, it's actually represented in time. So everything that I've shown you, I think I describe as having an X plane, a Y plane, and a Z plane, Z being down. We say Z is depth. It's always beneath our feet. The challenge with seismic is that it's actually represented in time. And so that's a little bit of a challenging thing to conceptualize, is how can you measure something in time? But we have to do a lot of heavy lifting to convert from time to depth based on things that are happening, like the changes in densities and velocities, fluid presence, lithologies, fault structures, all sorts of stuff. All of that goes into a model to convert into a depth model of seismic. Okay, so here's a seismic line. And what I'm going to do is I'm going to draw on this based on what I see as a geophysicist. Again, this is represented in time, two-way time. It's that travel time it takes for a wave to leave the source and hit receiver. And now there's things that we can extrapolate based on this view. Really, again, what we're looking at is a bunch of wavelets, and each little change in wavelet represents a change in density or something happening in the subsurface. So some of the things that my eye is drawn to right away are faults. Again, think about how this is a slice of the subsurface. Do you see the faults? Okay, let's see if I can draw a fault on here and maybe you'll see it. Okay. Now, can you see the faults? If this is a fault here, can you see another one? Here's another one right here. Any more? This looks like one. It may be something else happening over here. So I hope you can see those faults that I just drew. Now the next step is connecting these lines across the faults and how they look as we go from one direction to the next, as it crosses this fault, as it changes directions, and all sorts of complicated stuff. Actually, I just saw another little fault over here. This is kind of fun. Here's another fault here, and you can see its little counterpart here. Okay, so now let's draw across these faults. And this is a little bit challenging to do on the fly, but hopefully you can see some of these characteristics with me. Now, if I'm going to go from left to right, we can see that this is either a ground surface or a water surface. That's pretty easy to see. That's a very continuous line. There's nothing that's really disrupting this line. And if we go down, if we just look down from there and we try to see patterns across these faults, we can see that perhaps, this first dark line here looks something like this. And it does a little skip. That's the top of that fault. And we can see that it probably skips down here, something like this, okay? Something like that. We can do it for something deeper too. Let's just choose another one that looks like a pattern that is recognizable. See how these two lines look very similar to each other. So I'm going to do the one that's between that. That kind of looks like that. Something's happening there. And then it looks like maybe this, and it goes down, and so on and so forth. So maybe you can see some of these features. Basically, it's a little bit of like recognizing patterns and seeing patterns across faults and seeing disruptions in these different waves. And you can infer different things about the subsurface based on these observations. Now, it's challenging to do just on the fly, and this takes a long time, and we have a lot of software that helps create these images and helps geoscientists interpret this data. But that's a quick glimpse of what seismic data is and how we can use it to look for faults, look at different horizons, look at different layers in the subsurface, and ultimately use this to discover resources beneath the surface. Covered a little bit about seismic. Maybe we can move on to a different type of data that's very similar, and that's called ground penetrating radar. And I think I've mentioned this before throughout the lectures. It's a similar process to how seismic is acquired, except that instead of using sound waves, we use electromagnetic waves. And these are used at a much higher frequency. So when I just talked about seismic at being, somewhere around 20 hertz, electromagnetic waves are at much, much higher frequency, up to 1 gigahertz. Now, these types of principles are also used in the medical field, but we use it to look at what's beneath the surface as opposed to using an MRI or something to look at, like your internal organs or your bones and things like that. So similar to seismic, we have a source and receiver that emits electromagnetic waves that bounce off things in the subsurface. Now, electromagnetic waves react differently to things in the subsurface, like presence of fluid, more so than necessarily changes in velocities. So there's applications for GPR like archaeology, unexploded ordnance detection, groundwater detection, mapping, construction. And GPR is using electromagnetic waves, so it's sensitive to dielectric properties, which can show contrasts in soils and look at all sorts of different anomalies in the subsurface. So in my introduction, I talked a little bit about my background and my experience, and I used GPR as my master's thesis. And this is a picture of my setup for my field research. Again, we have a source and a receiver pair, and as it emits electromagnetic waves, it bounces off a subsurface reflector. This would be something like a change in dielectric properties, like it would be a fluid contact, for example. And we measure the time it takes for those waves to reach the receiver from the source. And one of the projects I did as an undergrad was looking for dinosaur bones in the subsurface using GPR. For my master's, I used GPR to look at internal dune structures of sand dunes. And and you can see here that the image is a little bit challenging to see. It's a little bit more challenging to decipher what's happening in the subsurface here. But what was interesting is that we were able to look at different types of deposits that are happening within a dune to try to understand how a dune is created, if there's different erosional surfaces and things like that that we could image using GPR. If you'd like to read my research, there's a link to it there. It's quite the fun reading for at night if you want to go to sleep, then I highly recommend it. Okay, so that's it on GPR, just a quick overview on that. But there's lots of other applications that's used for construction science, looking at bridge stability, groundwater detection, all sorts of things for GPR. It's a very cool tool. Okay, another tool that we use in geophysics is called DC resistivity. And DC resistivity and electrical resistivity tomography are surface methods where there's an electric current that's being injected from electrodes into the subsurface, and we can measure the resistance of flow. So it's helpful if we're trying to determine groundwater flow, which direction it's going on. If you don't have surface wells or if you don't have any groundwater wells, DC resistivity would be able to tell you that. And that's important if we have groundwater contamination. So earlier in the semester, we talked about how that's a really big deal. And you might be able to determine flow of groundwater so that you can do some more remediation if there is contaminants and things like that. So what happens is you have these measurements of current and voltage that show how resistive the subsurface is. And variations in fluid saturation, resistivity, rock types, porosity, all those things could tell you about how resistive the subsurface is. So here's an example of an apparent resistivity survey. And what this shows you is how resistive in the light pinks, something is very resistive, and then the greens are not resistive. So generally, we're looking at a very resistive section here. And the lightest colors here would show you that this is extremely resistive. This is, like a bedrock or something. And we see how there's if this is a river crossing, this might be some place where we would have fluid flow or change of fluids and things like that. So DC resistivity profile can help you determine fluid flow, bedrocks, subsurface layers, all sorts of things. Okay, so if you remember from earlier in the lecture, another method that we use is using magnetic anomalies. And this is a slide from way back then, where we learned about the Earth's magnetic field. And the Earth has a magnetic field that acts like a dipole, and the field actually changes. Its geographic north isn't always the same as magnetic north, and it flips and it moves. And as rocks form, they create their own magnetic field that aligns with the field at which they were formed at. So if you have a volcano that's erupting and it has magnetic material in it, it would align with the Earth's magnetic field at the time it was deposited. Now, as the magnetic field changes and rotates and shifts and flips, that rock is going to have a different magnetic field than the rocks around it. We can measure that. We can see those anomalies. So you can, and that's mostly used for mineral or metal detection. And this is a tool called a magnetometer. You can see this guy here is holding a magnetometer over his shoulder. This is actually quite difficult field work because it's heavy. You do a lot of walking. You can do land surveys. You can also do aeromagnetic surveys, which can be done over a much broader region. But what it looks at is the sensors here measure the Earth's magnetic field. And if there's differences between the current magnetic field and what's being read by the magnetometer, then we know that there's an anomaly there. And these can be used for things like archaeology, or lots of mining applications use magnetometer data. So here's an example of a magnetometer land survey. We can see how Mount Rainier, these would show where those volcanic eruptions took place, and they have a different magnetic characteristic than the surrounding rocks. We can also use this for archaeological aspects here. So this map shows prehistoric fire hearths. So there were some maybe fine metals or something associated with burning, or a higher carbon, or there's other materials associated with these fire hearths that showed up as an anomaly using magnetometer data. It's pretty cool. Okay, next is a gravimeter. Now, a gravimeter is an instrument used to measure the gravitational acceleration. And every mass has an associated gravitational potential, and the gradient of this potential is a force. A gravimeter measures the gravitational force. So here's what a gravimeter looks like. It's very sensitive. You can see that it has its own little tripod set up here. And it basically measures the gravity at that point. So if you have voids in the subsurface, it would show a change in the gravitational acceleration at that exact location. If you have something that is extremely dense below it, it would also change the gravitational acceleration. We can also do aero surveys, like from a plane, you'd be able to measure the gravity changes across a wider area. So here's a quick video of how to combine some of these data sets and how we evaluate the subsurface.
Geoscience Australia provides specialist advice responding to some of Australia's most important challenges, including understanding Australia's vast mineral, energy and groundwater resources. We're undertaking new research across Northern Australia to map potential resources buried deep below the Earth's surface. Australia's vast mineral wealth is still concealed underground. Around 80% of our landscape is underexplored. New geoscience information, tools and methods are required to unlock Australia's hidden resource wealth. Geoscience Australia carries out a number of geophysical surveys to investigate where resources are hosted underground. One technique used to identify mineral and groundwater resources is airborne electromagnetic, or AEM, surveys. Through the Exploring for the Future program, Geoscience Australia completed the world's largest AEM survey in the Northern Territory and Queensland. This type of survey is commonly used by industry to aid in mineral and groundwater exploration. An aircraft fitted with special equipment collects data from its sensors that image several hundred metres below the Earth's surface. The data is analysed into a 3D environment to better understand the geology of the survey area. When integrated with other data sets, it can reveal the location of potential mineral formations and map groundwater resources that can support communities, industries, and the environment. The results show conductive units that could indicate the presence of mineral deposits, such as nickel and other commodities. This provides explorers new insights and target areas for further investigations. New geoscience data and knowledge increases confidence in exploration investment, helping to grow Australia's resources sector and create more jobs for all Australians. Discover more about exploring for the future on our website ga.gov.au/EFTF.
So what I liked about that last video is that it combined a little bit explanation about aeromagnetic data, how it's used in conjunction with other types of data to create that image of the subsurface. And that's basically what geophysics is about. It's about using a variety of different disciplines and data, whether that's from computer modeling, physical data, geological data that we get from looking at rock samples and outcrops, trends, all sorts of things. All these pieces are integrated together. And that's basically what geophysics is. It's being an investigator, using a bunch of different data in a versatile field with all sorts of applications and putting the big pictures together. And that's why I think geophysics is a really cool discipline, because you don't necessarily have to be good at looking at rocks. You don't necessarily have to be great at understanding physics. But if you are good at a few of these things, if you do like chemistry, you do like programming, you do like engineering, you do like all these things, there's a place for you in geophysics. And that's why I'm so passionate about it. So this is a very simple scratch the surface of geophysics. And I hope that you learned something from this lecture, and maybe you can ask me more about geophysics because I can just talk your ear off forever about it. And that's it for this lecture.